Phased array antennas are one of the most powerful technologies behind modern wireless communication systems. From advanced radar to 5G networks and satellite internet, they allow antennas to steer beams electronically without any mechanical movement. In this video, we'll understand how phased array antennas work in simple terms and then connect that understanding to a real-world example. First, let's understand why we need phased array antennas. In traditional TV broadcasting, signals come from geostationary satellites orbiting about 36,000 kilometers above Earth. Since they rotate with the Earth, they appear fixed in the sky, so the dish only needs to be aligned once. However, their large distance causes high latency, making them less suitable for real-time internet applications. To reduce latency, modern systems use low Earth orbit (LEO) satellites which orbit much closer to Earth. Because of their lower altitude, the signal travel time is much shorter, resulting in lower latency and better performance for real-time applications. But LEO satellites introduce a new challenge. They are constantly moving relative to the Earth. Unlike geostationary satellites, they do not remain fixed in the sky. Therefore, the ground antenna must continuously track the satellite as it moves. One possible solution is to physically rotate the antenna using motors and mechanical tracking systems. However, mechanical systems are slower, less reliable over time, and require maintenance. Instead of physically moving the antenna, we can electronically steer the beam. And this is exactly where phased array antennas become extremely useful. A phased array antenna works very differently from a traditional dish antenna. Instead of using one large radiating element that must physically rotate to point toward a satellite, a phased array consists of many small antenna elements arranged in a line or a two-dimensional grid. Each element transmits or receives the same signal, but with a carefully controlled phase shift. These phase shifts cause the signals to combine constructively in one direction while cancelling in others. By simply adjusting the phase of each element, the antenna can electronically steer its beam without moving any mechanical parts. To understand how this electronic beam steering works, we first need to understand how electromagnetic waves travel through space. Imagine dropping a small stone into a calm pond. The ripples spread outward in expanding circles. Radio waves behave in a very similar way. When an antenna radiates energy, the electromagnetic wave initially spreads outward as a spherical wavefront. Close to the antenna, these wavefronts are strongly curved, and this region is called the near field. As the wave travels farther away, its radius becomes larger and larger, causing the curvature to gradually decrease. Eventually, over a relatively small area, the wavefront appears almost perfectly flat. At this point, it can be approximated as a plane wave, and this region is called the far field. This concept is particularly important in satellite communications because satellites are located extremely far from the Earth. By the time their signals reach a receiving antenna, the wavefronts are essentially plane waves rather than spherical waves. This allows us to analyze the received signals using simple geometric relationships. Now let's see how this helps us understand beam steering. For simplicity, consider a phased array consisting of only two antenna elements separated by a distance, d. First, suppose the incoming plane wave arrives exactly perpendicular to the antenna array. Since the wavefront is flat, it reaches both antenna elements at exactly the same instant. As a result, both antennas receive identical signals with the same phase. These signals pass through the receiver circuitry where they are amplified, filtered, and finally combined. Because they are perfectly aligned in phase, they add together through constructive interference, producing the maximum possible output signal. Now suppose the satellite moves, and the incoming wave arrives from some angle instead of straight ahead. This means it reaches the first antenna element slightly before it reaches the second. Even though this time difference is extremely small, often only a few picoseconds or nanoseconds, it creates a measurable phase difference This phase difference is created because one signal has to travel more distance as compared to the other. In this case, this phase difference is 140 degree. And if we combine these signals without any correction, then received signal will not be maximum and some of the energy will be wasted because of destructive interference. As a result, the combined signal becomes weaker, indicating that the antenna is no longer pointed toward the satellite. So how do we fix this? Before combining the signals, we insert a phase shifter into one of the signal paths. The phase shifter introduces an equal but opposite phase shift, bringing both signals back into alignment. Once their phases are synchronized again, the signals combine constructively, restoring the maximum received power. In other words, instead of physically rotating the antenna toward the satellite, we electronically delay one signal so that both signals appear to have arrived at exactly the same time. An important question still remains. How much phase shift is required to steer the beam at an angle theta? To answer this, we first calculate the extra distance that the wave must travel to reach the second antenna element. If the antenna elements are separated by a distance d, and the incoming wave arrives at an angle theta, the extra path length is simply the projection of the antenna spacing onto the direction of propagation. From simple trigonometry, the extra path length is L equals to d sine theta. Since electromagnetic waves repeat every wavelength lambda, this additional path corresponds to a phase difference given by delta phi equals to 2 pi over lambda. Now substitute the value of L into this equation. So, we have got the final relationship. In this equation, we already know distance between the antenna elements, wavelength, so we can easily calculate the required phase shift to steer the beam at an angle theta. This is one of the most important equations in phased array theory. It tells us exactly how much phase difference naturally exists between adjacent antenna elements for a signal arriving from a particular direction. By applying an equal and opposite phase shift electronically before combining the signals, all antenna elements become synchronized, allowing their signals to combine constructively and produce maximum gain in the desired direction. If we keep the element spacing half of wavelength, then this equation can be further simplified. If these phase shifts are continuously updated as the satellite moves across the sky, the antenna beam follows the satellite electronically without any motors or moving parts. Although we used only 2 antenna elements to explain the concept, real phased arrays contain dozens, hundreds, or even thousands of antenna elements. Each element receives its own carefully calculated phase shift so that all signals combine coherently. If every antenna element has exactly the same phase, the beam points straight out, perpendicular to the array. However, if a gradual phase progression is introduced across the elements, the beam tilts in the desired direction. The larger the phase progression, the farther the beam steers away from the center. This entire process happens electronically at nearly the speed of light, making beam steering extremely fast and highly reliable. There are 2 main types of phased arrays, passive and active. In a passive phased array, a single transmitter feeds all antenna elements through a network of phase shifters. In contrast, an active phased array provides each antenna element with its own transmit and receive module, including amplifiers and phase control circuitry. Although active arrays are more complex and expensive, they offer higher efficiency, better performance, greater reliability, and the ability to generate multiple independent beams simultaneously. A real-world example of this technology is Starlink. Unlike traditional satellite communication systems that rely on geostationary satellites appearing fixed in the sky, Starlink operates thousands of low Earth orbit satellites that move rapidly across the horizon. Because these satellites are constantly changing position, the user terminal must continuously track them. The Starlink user terminal, commonly called the Starlink dish, actually contains a flat panel phased array antenna. Hidden beneath its flat surface are hundreds of small antenna elements arranged in a grid. Instead of physically rotating to follow a satellite, the terminal electronically steers its beam toward whichever Starlink satellite is currently overhead. As one satellite moves out of range, the beam seamlessly switches to the next satellite without any mechanical movement.